I'm Shai, co-founder, CEO of Qruise. Now it's on. And I want to tell you about a software we're building that's intended to help people that build quantum computers. So what we're building is essentially a physicist, okay? So it's a piece of software intended for R&D organizations that are building new technologies that have really challenging physics at the core of it. So right now, our software is around a junior PhD student, but having an infinite supply of junior PhD students in the lab is also extremely useful. So we're doing quantum computing and all the modalities, so NV centers, trapped ion, Rydberg, superconducting, spin qubits, you name it. We're doing another technology that people kind of forgot is actually quantum, which is MRI imaging, right? It's originally NMR, nuclear magnetic resonance. People got scared of the word nuclear, but it's just a nuclear spin in a magnetic field. So we can do that. And we're going to do silicon photonics very soon, because people are using it for quantum computation and quantum communication. And after that, we're looking to do things that are actually not quantum at all, but that's down the line. So I'm going to start with a very specific example, so you see what we do. So this is work we did with Lior Ella, at the time director of research at Quantum Machines, now at Google Quantum. Quantum Machines makes these really elaborate signal generation boxes. You can control electrical signals down to the nanosecond and millivolt, synchronize dozens of channels to a few pico. And they were using a superconducting quantum CPU from Quantware. And they're trying to make it work, and things weren't behaving properly. They got frustrated after a couple months. They decided to see whether our software can help. So this is the way the system is supposed to behave. What you're seeing is smooth oscillations between two quantum states. One is blue, one is yellow. This is the way the system actually behaved, right? Nothing like the way it's supposed to. And the question is, what's going on? Now, in order to fix it, we need to understand it. And when a physicist says they understand something, what they mean is they know how to write down the equations. So we need to figure out how to simulate the equations, the right equations, to get the actual behavior of the system. And this is where our core idea comes from, on which we base the company, which is we figured out how to do simulations that are based on physics equations and can still learn from data. Generally speaking, when you talk about simulations, you either have neural nets that learn from anything or physics equations that just are. We managed to combine the two. And when you do, and our digital twin learns essentially from the second picture, what you get is this simulation. And you can see it mimics what's actually going on in the device very well. We learned 83 parameters from this one data, this one image. Right? Qubit frequencies, couplings, T1, T2, temperature, a lot of other things, and transfer function on the control lines. This very boring thing that an electrical signal goes from room temperature down to a superconducting chip at 0.03 Kelvin, things get warped. But our AI physicist didn't just say, hey, something's going wrong. It characterized exactly what was going on. And if you know exactly how the signal is distorted, you can pre-compensate for it. And when you do, this is how the system behaved. Okay? As you can see, very close to the ideal. Not perfect, there are still things to be done, right? But a very huge progress. Now, to kind of sum up, because this is an example that's just illustrative. What we did is we learned from existing data. We understood to very great detail, or the software did rather, what was going on, what was going right, and what was going wrong. And that translated very quickly to actionable information that people in the lab could implement. Okay? The really good physicists at Quantum Machines spent actually a few months trying to figure this out. The software ran for about 4 hours. Okay? So this is a very significant accelerator. And to tell you what Quantum Machines thought about it, they became our first reseller. And that's really non-trivial for Quantum Machines. They're not in the business of reselling stuff. They're in the business of building boxes and selling them. So what are we building, in the more general sense? So if you think of the work of an experimental physicist, you have a system and you have an hypothesis about what's going on. Based on the hypothesis, you plan what data to take, how to manipulate the system, and then you go to the system and you interact with it. You gather information. You then take this information and you use it to update your hypothesis, right? So this is kind of experimental physics in the most general sense. And this is exactly the same flow, but now applied to quantum computing or quantum sensing. And this is what we do, okay? So we have a highly, highly detailed digital twin, or more accurately, a framework for a digital twin that our customers fit to their system. It's not based on neural nets because we need to understand what's going on. Neural nets are completely opaque. We then go interact with the device, right? So this is software that's running at the customer's lab. So it interacts with the device. It gathers information. It takes care of stuff like bring up and et cetera. And then all the data is used to do model learning. Another way of thinking of model learning is debugging, right? We have debuggers for software. We don't have debugger for physics until now, okay? And once you have a very detailed model, a very accurate model, you can do a lot of other things. For example, you can take an error budget. An error budget is the detailed quantitative breakdown of infidelities in, let's say, quantum computing to their root physical causes. What are the problems that, as I don't have 100% fidelity, to what do they map? And once I have a quantitative breakdown of this, I know where to focus my R&D effort. Right? I don't need to guess whether I need to fix this or that. Okay? But you need a very detailed model that's very accurate and no simulation reality gap to do that. In MRI, by the way, the error budget translates to why is my resolution only 3 millimeters and not 0.001 millimeter. Right? You want to break that down, for example. And then you can also use the same idea to optimize the next generation devices. Now, we do all kinds of stuff around that's very relevant. So we do all the bring up, for example, all the automation of the bring up, the many dozens of steps you need to take what is a physics experiment into a working quantum computer. So we take care of that. You get plenty of dashboards that you can kind of go into the data, look at the specific fits. Sorry. You can even click on a link there and go into the source code and debug the experiment to see what's going wrong. And one very important thing is that everything that I've been discussing runs locally in the lab with no information going to Qruise. And for companies developing new technologies, this is critical, right? If you go to, for example, IBM Research, I've worked with them a lot. The network of IBM Research is isolated from the internal IBM network, not to mention the internet, right? So all this stuff has to be fully local. And for those thinking about getting a license, you can access your data regardless of whether you have a license. So you never lose access to the data. And so if this looks interesting to you, maybe you're developing quantum hardware, or maybe you're an investor, because we're raising our seed round, please talk to me. We have a booth here, and I'll be there after this session is done. Thank you very much.